Hi again, my name's Chris Harvey from Canterbury Christchurch University, back in my front garden to do some more summertime science, and today we're going to find out how we can describe nature in a mathematical way with a very famous equation. So let's get going. So one thing we'll need for my activity is something we can measure, some kind of organism that we can take measurements from. Now, as it so happens, an organism that's very common in my front garden is the garden snail, Helix aspersa. And it's common here in Dover because we have such calcareous soils, obviously the white cliffs, the chalky soil, that's what snails love. They need the calcium carbonate to build their shells. So there we go, that's little Buddy the snail, and I'm going to be collecting a whole bunch of them. We'll see how many I can get. I'm sure I can find more than 100. And I'm going to take measurements from them, and I'll explain more about that when we get to the table once I've done my collection. So, see you again in a couple of minutes. So, there we go. That's a bit more than 200 snails, I think. Don't worry, none of them will be harmed for this experiment. I'll put them all back in the garden once I'm done. So what I'm going to do now is I'm going to start measuring them. So let's see how I'm going to do that. Here's my little setup. I've got my snails in my bucket. I've got my notepad to take down my measurements. I've got a little ruler here, so I'm going to take a measurement of diameter. I'll show you how I'm going to do that in a second. And I have a little bucket down here where I can put the snails that I've already measured. I could be measuring a whole range of things for this snail, but I'm going to measure the diameter of the shell. I'm going to do that by placing the shell with the opening facing downwards, so the operculum facing downward, and I'm going to take a diameter measurement from one end of the shell over here to the other end over here. And that, in this case, as you can see, is going to be about 2.5 centimeters. Yep, there we go. So I'm going to do it for each of my snails. It's going to take me a while, so I'll see you again in a few minutes. So here we go, I've got all of my measurements done, 2 pages worth, I'd say probably a bit more than 200 measurements, and over here you can see the size range that I encountered. So that goes all the way from the left here, that one is about 3 centimeters long, or in diameter, that one's about 2.5 centimeters, and that one is just 1.6, 1.7, something like that. So that's the kind of size range we came across. Now let's see what happens if I put all these figures together and start analyzing the frequency of the individual measurements in the dataset. And by the way, just to reassure everyone, here we go. The snails being released back into the wild after helping us with our experiment. And you can see they're still quite chipper and happy. Bye-bye. So I'm in my office now, inside, and I've just entered the data that I collected for my snails into an Excel spreadsheet, which you can see here. So I've got my snail diameters. I put the measurements in millimeters. So 17 millimeters is 1.7 centimeters, for example. And as you can see, the smallest snail we had was about 1.7 centimeters in diameter. And if I go all the way down here, you'll see the largest one we had is about 33 millimeters, or 3.3 centimeters. So quite a range of sizes, and you can also see that I had about 230 measurements, which is quite a lot. Now, what we want to do is find out, we've got the range of the sizes from 17 millimeters to 33 millimeters. We want to find out how frequent are snails of a certain size in our sample of snails. So for example, we have one snail that is 17 millimeters in diameter. We have 3 that are 19 millimeters. We have, well, maybe 7, something like that. Yeah, 7 that are 20 millimeters, and so on and so forth. So what we can do is we can use that information, how often certain values appear, and plot those in a histogram, which is essentially a bar chart that tells us how often certain measurements appear in our sample. I'll show you how to do that on a piece of paper and without any computer or any software on your own if you want to do that. But what I'm going to do is I'm going to create my histogram in a computer just to kind of speed up the process. So I've entered my data into a piece of software called R, which helps me analyze and visualize data. And I'm first going to run the histogram command. So I'm going to take my data from the snails and create a histogram. And this is what it looks like. So as you can see, first of all, on the y-axis we have something called density, which essentially means the frequency, how often a certain measurement appears. So the higher up the y-axis, the more often that measurement appears. And on the x-axis we have the diameter of the snails, so the different sizes. As you can see, most of our snails had a size of around 25 millimeters or thereabouts. So this is what we call the peak of the distribution, and this is also the place where we would find usually the mean of our sample, the average size of the snails. Now, as you also notice, the further we go away from that middle value, that mean, the less frequent the snails become. So really large snails are very rare, very small snails are very rare, whereas the snails that are kind of a middle size are quite common. Now, this beautiful peak shape that we have here is something we can approximate with a function, a mathematical function, and that's called the Gaussian function. It creates a Gaussian curve. It's also called a bell-shaped curve or a normal distribution, and you'll see what that looks like in a moment when I run the command to add this curve. So if I just run this command, there we go. You'll see now it's added a nice bell-shaped curve to my data, and this is called the Gaussian curve. So you'll notice that the curve fits my data quite well. There's a few little deviations here and there, but overall this is a really good match for our data. And that's what I would have expected, because the Gaussian curve describes most variables that we find in nature. And I'll explain to you why that's so important for us and why that is really useful for us to analyze our data in the natural sciences when we head back outside. So I'll see you there in a second, and I'll tell you more about this Gaussian curve. Here we are again in the front garden, so let's talk for a bit about the histogram we just produced inside. Now, the bell-shaped curve we fit to that histogram is also called a Gaussian curve. It's named after a German mathematician and statistician, Carl Friedrich Gauss, and his discovery of this normal distribution curve was so important, so significant for the way we analyze data and the way we can make predictions from those data, that the German government put him on the 10 Deutschmark paper bill on the money before the euro. But he was so significant that every German child learned about him, and he was probably part of the curriculum across most of the world. Now, why was his discovery so important? Well, from a bell-shaped curve, the Gaussian curve, we can extrapolate from a sample of data to a larger population. So the sample I took today was some garden snails from my front garden in Dover. But from the bell-shaped curve, the Gaussian curve I fit to my histogram, I can predict that garden snails across the UK will mostly be about 2.5 centimeters in diameter, and a very small number will be larger than 3 centimeters in diameter, and a very small number will be less than 1.7 centimeters in diameter. So I can make predictions about what a population of organisms will look like from a very small sample. What's more than that, I can use the knowledge that most variables that I measure in nature should conform to this Gaussian curve to check for deviations from that Gaussian curve. So here's an example. I'm going to put up an image from a research paper that looked at the beak size of birds that were affected by a drought. Now, as you can see here, before the drought, the bird population, the beak size fit the Gaussian curve very beautifully, but after the drought there was a big drop in birds with the mean-sized beaks, with the average-sized beaks. So somehow the drought affected their food source in a way that really disadvantaged the birds with the average-sized beaks, and the ones with the really small or really large beaks were the ones that benefited. The other thing we can do is, if we have a histogram for two different samples, and we have the Gaussian curves that go with them, we can compare those samples. So for example, if I have a sample taken in Dover, here in Kent, and someone else has a sample of snails from Spain, and we compare their histograms, it'll look like this, for example, we can see in this case the Spanish snails seem to be much smaller than the Doverian snails, so maybe there's something going on there that we should investigate further. So the Gaussian curve is a very powerful tool for extrapolating from a small sample to a larger population, and then also comparing populations amongst each other. So, now that you know what a normal distribution is, what the bell-shaped curve or the Gaussian curve is, and how you create a histogram to kind of check for its presence in a variable that you've measured, let's give you an activity to do for yourself. So, as I mentioned earlier, in nature we find this normal distribution, this bell-shaped curve everywhere in all kinds of variables to do with all kinds of organisms. So for example, here I have a grapevine that's growing outside our house, and if I went along and for example, I took some of these leaves here and measured the diameter of these leaves across the whole plant, or a sample of them, maybe 50 or 100 of them, I would probably find that their diameter would also fit a bell-shaped curve if I plotted a histogram, like I did with the snails. I could do something else. I could look at these clusters of flowers, right? That will make the grapes. I could count the number of flowers on each of these little sprigs. There's different sized ones, right? So they had different numbers of flowers in each one. So I could count those, and if I count enough of them, if I count 30 or 40 of them, do a histogram of them, right? How often a certain number of flowers will occur. That will also, or should also, fit a bell-shaped curve, a normal distribution. So here's your challenge. Go out to your garden or to your front porch, or if you don't have a garden or a porch, go out to the park where you walk your dog, or some place close by where you can safely socially distance, and just do some exploration. Pick something that you can measure. Take a measuring tape, take I don't know, a weighing scale, take something that you can take some measurements with. Pick something you can start measuring, and then take some measurements. I'd say 20 or 30 measurements should be enough to do a histogram and start to get a clue of whether or not what you've measured actually follows a normal distribution, a bell-shaped curve. Most of the times it will, and that'll be really interesting because you're confirming the principle of this normal distribution applying to natural organisms, but sometimes it won't. And if it doesn't, that could be something interesting going on there, and you might want to do some further research. So, go out, do some exploration, do some measurements of your own, plot a histogram. Like I mentioned earlier, I will put a description of how to do your histogram without the aid of a computer or anything else at the end of this video, and see what you come up with. So have some fun. I'll see you next time. Take care. Bye-bye. In this part of the video, I'm going to quickly show you how you can do a histogram without a computer or anything, or calculator or anything like that. All you need is a piece of paper, essentially, your data that you recorded from your organisms, in my case the snail shell diameters. So what I've done here is I've created a page where I've created a little table with all of my little, with the various different categories of measurement. So some snails are 1.7 millimeters, 1.7 centimeters, 1.8, 1.9, 2.0, and so forth. So what I can do now is I can go through my list of data and start tallying up how many snails fit into each of these categories. So the first snail, for example, is 2.8 centimeters in diameter. So I can go to my 2.8 centimeters here and make a dash, make a line for that snail. The next one is 2.6. That means a dash in the 2.6. The next one is 2.3, and so on and so forth. So what I can do is I can quickly build up a whole set of figures for various different shell sizes, right? So let's just imagine we end up with this kind of data set here. So we've got a nice set of numbers for each different category, a nice number of counts, and you can already see how this almost represents a histogram in and of itself. If I turn it on its side, right, that looks like a bit like a histogram. So what we want to do now is all we have to do is plot a graph, essentially, where we take these numbers here and put them on the x-axis, so that'll look a bit like this, and we'll start with 1.7, 1.8, and so on and so forth. And then we tally up, we take the numbers, so in this case 1.9 would have a total of 3, 2.0 would have a total of 5, 2.1 would have a total of 7, and so on and so forth. And we can then plot on the y-axis the frequency, so that would be f for frequency, so that would be 5, 10, 15, and so on. So we can start plotting the different bars. So you might have for, let's say for 2.0, let's go on to 2.0. Okay, 2.0 we had 5, so 2.0 we'd have a bar that goes up to the 5 mark, right? 5 across, there we go. 2.1, we've got a bar that goes up to 7, and so on. And so you build the histogram like so, in a nice hand-drawn graph. So that's another way of doing a histogram without the need of a computer or a calculator or anything else.